Switchable adhesives capable of high adhesion and easy release are needed for applications including robotic grippers, perching unmanned aerial vehicles, and climbing robots. These hybrid adhesives use Gecko-Like adhesive strength enhanced by electrostatic adhesion. Strength of the Gecko-Like adhesive depends on the real contact area between the microstructures and the substrate, while the electroadhesive component provides a normal preload, further increasing the contact area. This research explores the effect of bending compliance on hybrid electrostatic Gecko-Like adhesive scalability. We compare the adhesion pressures of non-compliant hybrid adhesives of various sizes with novel compliant adhesives and demonstrate that large area compliant adhesives outperform non-compliant adhesives on rough surfaces. It was previously shown that the maximum adhesion capacity of such adhesives is determined by the stored elastic energy. That is, lower the stored strain energy, higher the adhesion. However, adhesion capacity also depends on the real contact area, and the trade-off between the area and the stiffness has not yet been explored. Under ideal conditions, the contact area of a flat elastomer adhesive on a smooth substrate is equal to the pad's area. However, on rough surfaces, the contact area depends on the compliance of the structure and will increase with increasing compliance. This is even more significant in the presence of an electrostatic preload. Overall bending compliance can be increased by increasing the adhesive's area and decreasing composite stiffness. Previous work on flat films demonstrated that for equivalent contact area, shear adhesion strength is proportional to the inverse square root of the shear compliance of the adhesive. Experiments between hybrid adhesives of similar bending compliance and varying shear compliance demonstrated that holding contact area constant and increasing shear stiffness increases shear adhesion capacity. The non-compliant adhesive design is comprised of a double-sided electrostatic component and resin insulator. The compliant design uses a single-sided interdigitated electrode pattern and a silicone elastomer insulator. Both bending compliance and shear stiffness are dependent on similar design and material choices. As a result, high bending compliance contributes to larger contact area but low shear stiffness and high stored elastic energy. On small area pads, this results in reduced adhesion strength in compliant designs as compared to non-compliant designs. On large area adhesives, the benefit of higher overall contact area due to high bending compliance negates the effect of high stored elastic energy, thus resulting in improved performance of compliant adhesives as compared to non-compliant adhesives. Our work demonstrates that the adhesive's design strategy and material choice may depend on the size of the intended device.